Right then, so basically it does this. That was it. That was a dim bulb tester doing what dim bulb testers do. So what does a dim bulb tester do? It's something I've mentioned a few times in my videos. So for instance, like this amp in front of me here, this is what's connected to the dim bulb tester. And all I did when I made the dim bulb tester flash was just turn this amp on. So, you know, how? Why? What is the point of it? Well, I guess I'm going to have to get the pen out and just do a little drawing here because it makes things a little bit simpler. Well, easier to understand anyway. Let's see how well this works out, trying to work with the tripod in front of me. So, basically, we have a load. So let's say in this instance, we'll have our mains wire coming in. We'll go to a switch. Let's make it a dual pole switch. So let's say that one is live, that one is neutral. And let's say that goes to a transformer. And that's our transformer. It's a step down transformer. And that's going off to the rest of our amplifier circuit. Excuse me. So, if I've just worked on this amplifier, I apply mains and shut this switch, I'm limited purely by the resistance of the mains really and the transformer if there's something not right in this amp yet. Or if I've done something slightly wrong, it's going to get a huge amount of power and it's going to go up in smoke. It usually happens so quick you don't even have a chance to react. Many a time I've powered something up and transistors are blown apart, the magic smoke has escaped, and the thing you tried to fix now needs even more work on it than what it originally did when you first got it. So a dim bulb tester, simply if we get a light bulb, so let's do the old-fashioned, that's a nice light bulb, and all we're doing is let's say this is our mains, so this is our live, this is our neutral, the mains. That's all we're doing. We are putting a light bulb in series with our load. Now, for instance, the light bulb in my dim bulb tester, it's a 240 volt halogen bulb and it is rated at 105 watts. It's the equivalent of like 140 or something, but that's irrelevant. What we want to know is what is its actual power dissipation when it is on. Now, light bulbs, because they get so hot, they have a considerable change in resistance. So any standard conductor, as you heat it up, its resistance will increase. Various different materials go through different rates of change, and you know, there's certain semiconductors and various other appliances that don't follow this rule, but for standard conductors, an increase in temperature also corresponds to an increase in resistance. Now I've measured this light bulb, and cold, it is 36, nearly drew a G there, ohms of resistance. And I can't measure the hot resistance because, you know, it's hot and it's got 240 volts across it. What I can do is use Ohm's law to determine what the hot resistance must be. And if you do the maths and say, well, it's 240 volts, it's dissipating 105 watts, then it must be drawing 0.44 amps of current. So you then say 240 volts divided by 0.44 amps gives you 545 ohms. So when it's hot. And if you was to do some other maths, the maximum peak current, if you turned this light bulb on, well, we'll use peak current on 240 volts, not 340, but if you was to say the RMS current it could pass, if it didn't get warm, well, at 36 ohms, that would be 6.6 amps. And at 545 ohms when it's hot, it can only pass 0.44 amps of current. So what happens is, for instance, when I turned it on and when I turned this amp on and it briefly flicked, because there's power supplies and stuff in this amp, capacitors that need to charge, they're seen as very low impedance. They require a very high amount of current to charge them up. So as I close this circuit, the transformer energizes, the power supply starts to charge, and it starts to try and draw a quick pulse of current off the mains. Well, the light bulb had already limited that to a relatively low value, but within a few cycles of mains, the light bulb starts to warm up. Its resistance increases. There's a delta time temperature increase thing at any given current through it. As its resistance increases, as it warms up, its resistance increases. That causes a basic, Ohm's law again says that power in any device can be equated as current squared times resistance. We call it I2R. So you can basically say if there is 1 amp passing through something, well, 1 squared is 1 and its resistance is 10 ohms, there will be 10 watts. If there's 2 amps passing through something, well, 2 times 2 is 4, its resistance is 10 ohms, it would be 40 watts. So if this is trying to carry on drawing a current pulse, this light bulb starts to warm up, its resistance increases, therefore that amount of current through it forces it to get even hotter, its resistance increases, and at some point its resistance starts to increase so much that the voltage across this point, the load, starts to decrease significantly. So therefore the current being drawn by the load also starts to decrease, and at some point an equilibrium will be reached where the light bulb will either be glowing quite brightly or just dimly. It's losing, when it's very dim, it might only be losing 10 to 20 volts across it, and this still has the majority of the voltage. But as you start to draw power through this circuit, as it wants more current, the voltage across this increases and the voltage across this decreases. And if you basically try to short out these 2 terminals here with the switch closed, instead of there being a loud explosion and lots of arcing, basically the light bulb would just go to full brightness and there'd be no voltage across these terminals anymore, and it would all be across the light bulb. It's a very, very handy thing to have when testing equipment. So I'll show you it doing something. I'm going to simulate a fault condition in the amplifier that's in front of me, so this amp here. And if you actually watched the video where I was working on this, I had the dim bulb on it and I got the dim bulb to come up to brightness. And what actually happened is this tab on this transistor is at plus 35 volts DC. It's at the positive rail voltage. This heatsink is earthed, grounded, whichever term you like to use. And if you notice the little not the screwdriver, the meter probe I had, it slipped out there and it actually ended up going through this transistor, and where that black spot is just on this metal clamp here, that's actually where it arced to. It arced the power supply, it shorted the power supply out. There was a small arc as the capacitors discharged, but the dim bulb just instantly came up and it stopped nastiness happening. In this instance, I should doubt the amp would have been hurt. It's more likely it would have just blown the fuse in the power supply. So what I'm going to do is I'm literally going to shove that through there, like that, onto there. Oh, don't want to bend that transistor too much now, do I? And I'm literally just going to simulate that same fall, just like that. So bear with me where I just set the dim bulb tester back up, because I unplugged it to do some resistance readings. Back in a moment. Right, I think I've got everything in shot here. So here's the amplifier connected to the dim bulb tester. Dim bulb tester is the lamp up there. If you're wondering why it's a lamp over there, it's because when I'm not using it as part of the dim bulb tester, it's just another lamp in this room. It gives me more light. I've got 4 light sources in this room. It's very nice to work under. It sort of helps do away with shadows. But yeah, when it's not being used as a dim bulb tester, there's a bulb just on top of that speaker at the base of that lamp, LED bulb. That gets put in it and it just goes back to being a lamp. So here we are. Here I am with my simulated fault condition. So let's say I've done some work on this amplifier and I haven't noticed that there's a shorted transistor and it's shorting. Say for instance one of the actual output transistors in here, if it was shorted, it would be trying to short the collector to the emitter, which would be the same as trying to short the top of the power supply to the 0V point, just like I've done now. Watch what happens when I turn this on. That's it. The dim bulb is, my power supply is not being hurt. dim bulb tester has just come to full brightness, and it will just sit there, and it's a really good visual indication as well that there is an issue with something, because straight away, instead of starting to probe and find voltage and stuff, you can see that straight away and go, right, something's up, I'm going to shut it down. So I'm going to shut that down. I'm just going to get another meter out, and I'm going to measure what the actual voltage is in my power supply and coming into the amplifier with that shorty condition left like that. So you can see here I've just replaced the probe with a jumper terminal. I've got my meter out, and so I am just going to measure. So again, my dim bulbs come up, so let's measure the power supply voltage at the amplifier. They are 0.6 volts. That's, instead of there being the 35 volts, there's 0.6 volts. And let's see if I can take an AC measurement at the actual transformer primary. So that is what the input voltage is being limited to, 32 volts. So there's going to be about 210 volts across the light bulb, 32 volts across the input to a transformer, and then with transformer losses and internal resistance and stuff, the output is just a mere 0.6 volts. So the transformer isn't having a particularly hard time realistically, because like I said, it's, if you start crunching the numbers, well, at full heat it's going to be 545 ohms, so there's only going to be less than half an amp in this transformer primary, and so, you know, it's going to be, maybe it's going to be hard to, I can't give you a definitive figure unless I actually get a current meter out and measure the current going through the bulb to tell you what its resistance is at the voltage across it. But at 210 volts, and the fact it's still glowing quite bright white, you'd probably imagine it's somewhere around the 500 ohm marks. It's probably passing somewhere around half an amp. It's yeah, so, but ultimately it's stopping any damage being done. And if I, so you can see it going away there, if I remove the wire link off my power supply to earth, the amp fires up. The dim bulb doesn't quite go out. I'll see if I can zoom in on it. Probably turn some other lights off, it would be handier. But this is where it gets its name from. If I turn the other lights off, it'll be a bit easier to see what's going on. It's called a dim bulb tester because when things are working normally and they're just drawing a very low amount of current, it's a small voltage across the bulb, it's just glowing dimly, and that is why it's called a dim bulb tester. So let's have some light back on in here, shall we? So yeah, I guess I'll just run through how I made my one and how the standard way is of doing it then. How is a dim bulb tester wired up? So I will just say here, this isn't an instructional video. If you don't know what you're doing with mains wiring, just stay away from it. It's lethal, especially in the UK. We have 240 volts, 230 volts, 220 volts, depending on a whole manner of regions, time of day, and various bits and bobs. I think I've measured it right down at about 215 and up to nearly 250 at times. So yeah, it's just call it 240 volts. So yeah, this isn't an instructional video. By no means mess around with things like this if you don't know what you're doing, because it's lethal. But here's my one. I've written on it that it's a dim bulb tester. I've missed the N off extension for some reason. Dim bulb tester, not extentio lead. Who knows? I've marked on here the side the bulb plugs into and the side the load plugs into. Because I've used a dual gang socket, I've had to cut the internal link where, so you've got your three connections inside for your wire, the earth, the live and the neutral. I've had to cut the internal link for the neutral because you only connect it at one point and there's an internal links between the two sockets. Neutral still connects into the wire it should connect into, which connects to this pin. Where I cut it, I had to solder the live coming into this pin, and the wire link still is in place for these terminals. And yeah, I can't remember where I connected live to. Yeah, live connects to there. Yeah, so yeah, there is, yeah, the live terminal on the back of the plug isn't actually connects to anything anymore. Yeah, just a bit of brain freeze there. So yes, it isn't good really doing it this way. I had to do it that way because I used a single dual gang plug. So the the earth pin on the plug that plugs into the wall connects direct to these two earths. The neutral terminal, this one, connects direct to this neutral. And the live pin connects to the wrong side, which isn't great. It wouldn't really be an issue unless I kind of took this out of the house and someone decided to try and use it as an extension lead, even though it says not to, and plugged it into the wall and then plugged their appliance into here, and then for some reason decided to take the top off their appliance, and then for some reason decided they'd touch the live mains wiring because they was only touching the neutral and thought it would be okay. They would then be touching the live. But just for the sake of thoroughness, you never want any conductors to have a color coding which doesn't match the actual voltage inside of them. And so with mains wiring in the UK, brown is live, blue is neutral. The phasing is correct for the load. Live goes into live, neutral goes into neutral. So as long as the wiring in the actual appliance I'm working on is correct, the polarity of the wires inside are correct. So yeah, that's my one, just a dual gang socket, and maybe a meter and a half of wiring, and I literally, the IEC lead from the amplifier just plugs in to the load terminal, and the light bulb from the lamp plugs into the one marked bulb. So internally, wiring wise, most people, like I said, would a basic one would do, say, 2 single gang sockets on a piece of wood. You're coming from the mains. Earth wire from the mains will connect to the earth connection in the first socket. The live wire from the mains will connect to the live connection in the first socket, and you'd have to have a neutral block connector in that socket for the neutral from the mains to connect into. You have a link wire between the two sockets. The neutral for that socket goes through the link wire into your block connector here, so neutral from the mains connects straight to neutral on your second socket. The neutral terminal on your first socket, so you can see the first socket, the live comes in, it goes up to the light bulb, comes back down to a neutral terminal. So your link here, your neutral terminal connects to the live on this second socket. And like I said, the earths connect between the two. So the polarity of the wiring is still correct, but instead of this one being a neutral out, it's now just the live return from your bulb. It's not an issue because, again, you mark it up. You make sure it's kept safe and out of the way. It just means when both things are plugged in, the polarity on both of them are correct. Technically, if you unplug this one, if you follow it, your live will be going up to your load for your neutral. No, sorry, no, won't be any live going up to your load. Yeah, no, I'm wrong there. I was just thinking it could backfeed, but it can't because the only connection to this live is via this plug socket. So yes, this is a much better way of doing it than how I have done it. Other ways of doing it are to put the light bulb holder socket on a piece of wood, and yeah, where you just wire into your bulb, come out your bulb to your live, your neutral goes to your neutral, earth to your earth, and you can put a bypass switch in, so instead of having to unplug your appliances, you can just flick the switch and bypass the dim bulb. On this one, if you want, you can make a plug which has a wire link from live to neutral in it, and that bypasses it when you plug it in. However, that's definitely the kind of thing you don't want lying around, because if someone plugs that into a normal socket, you've just shorted live to neutral. Other things you can do are, you know, if you wanted like a real full versatile proper piece of robust test equipment, current limited supply, you would have a fuse, a dual pole switch, a proper 1-to-1 ratio isolation transformer. You'd have a variac. That's probably not how you draw a variac, but a variac is basically just an auto transformer with a terminal that moves up and down the winding, so you can vary the actual voltage out of it. The reason you don't just have that, because it isn't an isolation transformer, there's still direct connections through this winding across to your load. So that would sit after your isolation transformer. And you can then again come into, this could all be on like one socket, on like one plate, or in its one like nice, you know, you could turn an old amplifier housing or something into it with just a control sticking out the top. And yeah, and it then go to your bulb, your bypass switch and your socket. So you've got, you know, you can ramp up your voltage with your variac with your bulb in series, and you can see if your bulb's lighting up or not, and if, you know, say for some certain instances like valve amplifiers and stuff, draw a lot of standing current even on idle, and you can't really test them with your bulb in circuit, but you can ramp the voltage up, give you an idea if everything's okay, and you can then turn the voltage down and bypass the bulb and then measure again and then slowly ramp your voltage back up to where it wants to be. It'd be a very robust piece of test equipment. Because it's got the isolation transformer, it breaks, especially in England. We have the PME system where earth and neutral are tied together. So it breaks that connection. So if you happen to touch something live, instead of it now being at mains potential against the earth via you, it's open circuit. There are some instances where you might want a center tap transformer and actually connect earth to it. And I know that sounds a bit weird because you can now get a shock off either one of these two wires, but there are reasons you might want to do that. The general way would be just to connect earth straight to this socket, so your appliances are still referenced to mains earth. But then again, there are some instances where you wouldn't want that and you want it fully floating. Yeah, I'm not here to deal with those. I'm just saying there are, if you ever see like isolation circuits, and you see like it's wired a certain way, it doesn't necessarily mean it's the way you want it wired. Someone could have wired it that way for a very specific reason. So just be careful if you're building something like that and you're going off someone's design plans. So yeah, that is it really. Just basics on a dim bulb tester and what they do and how they work. And like I said, it's not meant to be an instructional video on building one. It's just an educational video on what they do and why we use them. And yeah, if you are building one and you know, well practicing mains wiring, you're confident what you're doing, just be safe, double check, triple check, quadruple check everything. And yeah, just always be careful where you're sticking your fingers. I find a good rule to tell someone when it comes to messing about with something they don't know, whether it be mechanical, electrical, all manner of bits and bobs, is don't stick your fingers where you wouldn't put your penis. It's a pretty good way to either keep everything intact at the end of the day or keep yourself alive. But hey, that's just from my point of view. But anyway, as always, thanks for watching. I hope this video has been some use to you and catch you next time.